Hello, everyone. My name is Eric Nye,
I'm Ian Lamb.
I'm Patrick Liu.
and we're the team from Middlesex School, and we're going to present our solution for problem A, introducing stress. So first, let's introduce this problem. So we're considering the relationship of the stress of new crew members and existing crew members in International Space Station. And we're considering the influence and relationship between the stress and productivity of each group throughout the time. And we want to use differential equations to model these three potential scenarios: an immediate high work level, a short period of rest followed by a sharp rise in work level, and a gradual increase from low to high levels of work. And we have assumptions as below. We can divide stress into three categories, which are acute stress, episodic acute stress, and chronic stress. And we also assume that all crewmates experience the same stress level from each stimulus. And we consider Yerkes-Dodson law, which moderate stress levels lead to highest productivity. And all crewmates have the same optimal stress level and productivity throughout time. We then define these variables, the time passed, total time, and we make the function of work over time. And then we have the size of each group. And then we calculated the average stress and average productivity of the two groups from the stress of each group.
So again, to model stress, we have three types: chronic acute and episodic acute. So to find our derivative of stress, we simply add the derivative of these three over time. And then for the stress of the existing crewmates, we also subtract A, which represents the rate at which they adjust to the influx of workers. And for new crewmates, we subtract B to represent the rate at which they adjust to the new environment and launch stress. So to model chronic stress, we have dSC over dt equals CSE. In other words, it's proportional to total stress. And then we model acute stress by keeping it proportional to increases in work, as shown. And then to model episodic acute stress, we take like this sum of all the work done at certain times, except we also multiply it by a scale factor as shown by the diagram here that decreases linearly as we go further away back in time. And from the second diagram on the right, we obtain the following equation for the derivative of the episodic acute stress. And to recap, here are our equations for changes in stress, and then ds over dt is just the weighted average of this SE and SN.
All right, so for modeling productivity, we consider the Yerkes-Dodson law, which states that the graph of productivity over stress is like a bell curve. And instead of using a normal distribution for this, we used a parabola because it's simpler and simplifies our model slightly. So for a parabola with vertex F and G, where F and G are the optimal stress level and maximum productivity respectively, we get that the rate of productivity over change in stress is given by the following equation, which is just a parabola. And we can use the chain rule. dPe over dt is equal to dPe over dSE times dSE over dt to model productivity change with relation to time. And a summary, so productivity of existing crewmate and the productivity of new crewmates are modeled in the same way. And dP over dt is just the weighted average of these quantities. So here are three work functions. The blue line represents a high level of work immediately. The orange line represents a short rest followed by an immediate increase in productivity, and the yellow line represents a constant increase in work.
So we first model scenario 1, which is when there is an immediately heavy workload. And in this case, we consider the work function as a constant line. Here, we also put our parameters for without new crewmates and with new crewmates. So for the work function, we made the case when there is without new crewmates twice as much as the case when there's with new crewmates. And we made the SE0 240 for with new crewmates because it's close to the breaking point when the work is going to overwhelm all the crew members. We also have parameter A defined here to represent the rate at which the existing crew members are getting used to the incoming new crew members. And for the rest of the parameters, we made them equally weighted because we assume that there is same stress tolerance among the crew members and the same level of outside sources influence in different scenarios. And here are the two graphs we got from MATLAB. The first one being the stress level over time, and the second one is the productivity over time. And in these two graphs, the blue line represent the stress or productivity before new crewmates coming in, and the purple lines represent the case after the new crewmates coming in. And in the first graph, we can see that the stress level after the new crewmates come in are actually way higher than the stress level before new crewmates come in. And on the second graph, we could see that the average productivity after the new crewmates come in are holding at the really low level compared to the case when it's before new crewmates come in. So actually, this result turns out to be the worst in case of maximizing the productivity and minimizing the stress.
Yeah, so here's our second scenario. So here's for a short rest followed by a sharp rise in workload. And again, we model this with a logistic curve. And so in order to keep the integral of WT for without new crewmates at 1, we say that the inflection point happens when x equals 20. And we say that the maximum of this logistic curve is 1 over 20. And we set all the parameters, all the other parameters very similarly to what we did before to keep things constant. And then looking at our graph generated by MATLAB, as we could see, this one has a very distinctive V shape on the left for each of these curves. And that's because once we reach the half-life of the logistic curve, all of a sudden we have a sharp increase of work, and that causes both increases in chronic stress, increases in acute stress, and episodic acute stress. So all three stressors suddenly increase, and so that's why we see this sudden shift upwards. And then as we could see again, the stress level before, like if we don't have the addition of new crewmates, is still significantly lower than the stress level that new crewmates. And this one actually turns out to be the best scenario in terms of minimizing stress and maximizing productivity.
So for scenario 3, which is a gradual increase in workload, we use a linear function of work to model this, and the other parameters are held the same as in the other two scenarios. So as we can see, the stress level gradually increases over time for each of the 4 lines. And this makes sense because as the workload gradually increases over time, acute stress and episodic acute stress also gradually increase over time. And in conclusion, from all 3 scenarios, adding new crew members adds too much stress. As in each scenario, the total stress without new crew members was always lower than with new crew members. Scenario 2, minimizes stress and maximizes productivity, which we can see from the table on the right. And scenario 1 maximizes stress and minimizes productivity. And just a few limitations of our model. We made a lot of assumptions, and our model is a little general, overly general, and also our parameters were not precisely picked or backed using research.